Hey guys, today we got a new number, natural base E. E is a very famous irrational number, the second most irrational number in the world. Only pi has a beat. Next slide, I'm going to show you what E is. Now, when I say irrational numbers are numbers that never stop. They never terminate. They keep on going forever and ever. The decimal part does. Never repeats either. There's no repeating pattern. E is 2.71828182848, and it keeps on going and going and going forever. Okay, so that's the value of E. Now keep in mind, E is not a variable. E is like 2.7. Okay, and it's not really 2.7. Like we say pi is 3.14 a lot of times, which is not. Just an estimate. Okay, it's like 2.718 is about what E is. Now, E works just like any other number does. All your exponent rules work. Like this first example, E cubed times E to the 6. We're just going to add the exponents like we always do. All right, same thing on part B here. 16 divided by 4 is 4. The bigger E is in the numerator, so I would say 4E. And you can also punch that in your calculator and get an exact value for what E to the 9th is, or what 4 times E is. Not an exact value, but a decimal, kind of a decimal approximation, not even equivalent, because you can't really get an exact answer for a rational number. Same rules here. That 2 applies to everything, so I would do 3 squared is 9. I would raise E. You multiply the exponents together. Remember, don't leave a negative exponents in there. So flip the E to the bottom, and you get that right there. So everything we've done before also works with E, mainly because E is just a number. It's just an irrational number. All right, the graphs of them. You're going to see functions like this today. And don't forget, E is like 2.7. That's a big deal because that means it's a positive number. And remember when we did a positive base, the graph was exponential growth like this. So when when the exponent is positive, or when the exponent is positive, E is a positive number, and the graph's going to be exponential growth. Still goes past through 0, 1. The other thing we're going to do is we're going to plug in 1 or whatever number. We'll plug in 1. And if it's just that, there's E, 2.718, so we went over 1 up to 2.718. That was not that clear, I'm sorry. Let's try it on the decay. Look at E on this case. E has a negative exponent, which means it's really 1 over E. Okay, the graph's been flipped. Remember, if you put a negative in for the X inside, remember, negative inside is a reflection across the Y-axis. Look at the two graphs. They're just reflected across the y-axis. So now if we plug in 1, you get some really small decimal. And here's the deal. If you were to plug in -1, then you would get 2.718. Because if you put a -1 in there, same thing as plugging 1 into that one. Okay, so hope that makes a little bit of sense. It's all about A and what R is. And we'll look at a graph or two here in a second. Like right now. Okay, first one, tell whether each function represents growth or decay, then graph it. Okay, so this first one is definitely growth because the exponent is positive. So it says to graph it. If I plug in, watch, be careful here. That 3 means there's a vertical stretch. So if I plug in 0 for that x, remember anything to the 0 power is 1. And if I do 1 times 3, I get 3. So it's going to cross at 0, 3. And again, it usually crosses there at 1. But because the 3 is there, it's been vertically stretched by 3. Now I'm going to plug in 1. I'm going to plug in one more point. I'm going to plug in 1 there. And I would get E times 3. And if I do 3 times E the first power, I'm getting 8.15. It's going to go 1, 2, 3, 4, 5, 6, 7, 8 in just a little bit. So remember what the graph does is exponential growth. So it's going to get closer here, go up steep through my 2 points. And that's what I'll be looking for on Friday. All right, second one. Do the same thing, plug in a couple points here. I'm going to plug in 0 for x, which means that exponent becomes 0. There's nothing in front of the e, so there's no vertical stretch. It's going to cross right at 1, just like the other exponential functions we did. So I plugged in 0, got 1. Now, if I plug in 1 on this one, I'm really going to get e to the -0.5 power. So it's about to plug in and see what happens there. When I plug that in, I'm getting 0.606, so a little bit more than a half, like right there if I plugged in 1. And also if I plugged in -1 there, I would basically get e to the 0.5 power. And the graph's going to go like this, exponential decay. All right. You can also do compound interest like we did yesterday with E. And you can do it with E when it is compounded continuously, which sounds crazy. But the formula is great. A lot of people call it the PERT formula. A still stands for final amount. P still stands for how much you start with the principal. E is the number E. R is your interest rate and T is for time. There's no N this time because we're not compounding a certain amount of times per year. We're compounding continuously. It never stops compounding. So if you see this word, compounding continuously, we're using PERT instead of this, which we spent a lot of time talking about yesterday. Okay, so continuously. I'm going to show you one example. You deposit $42.50 in an account that earns 5% interest compounded. There's the word, continuously. How much is it worth after 10 years? Okay, so here it goes. The amount is the principal, which is what you start with, times E to the RT power. The rate is 0.05 and the time is 10 years. And I'm going to punch it in my calculator just like that and see what we get. And nice, after 10 years, it is worth $7,007, right? Which means it earned up basically almost $3,000, almost doubled in 10 years, which is that's good stuff right there. So that's what we're doing tomorrow. A bunch of E's. Remember, E is 2.71828. Keeps on going forever. It's just a number, kind of like pi, irrational. We can do all the things with it we did with other numbers. So just be ready for that. And I'll see you then. Bye.